Alrighty, let's take a look at how standing waves are created and derive an expression to figure out what sort of frequencies will produce standing waves, and this will have huge implications on music, in particular the notes that are made by a musical instrument. So we'll fill in our blanks here. Under specific conditions, reflected waves will interfere with incoming waves to create a pattern called a standing wave. So as we saw before, the standing wave is created as waves overlap each other in two different directions. So typically this could happen in like a string on a guitar or a violin. We have a couple of places of importance here. We've got what's called a node, a place where the particles experience node displacement. So as waves pass through each other, this will be a place where we always have constructive interference, as opposed to our antinode, which is our place where the particles will experience maximum displacement. So this is the big lumps that we see moving up and down. Now it's important to recognize that antinodes also experience destructive interference. At times the rope has to go flat between becoming a crest and a trough, but the nodes will always experience destructive interference. So in our drawings we're going to note the node with a capital N and the antinode with a capital A, so we can label those on our drawing. So today what we're going to do, we're just going to focus on drawing these patterns for a string that is fixed at both ends. So this is all musical instruments. I can't really think of an example of a musical instrument that has a string that's flopping around. You just wouldn't be able to stretch it tight enough to produce a tone. So for a string fixed at both ends, what we're going to do is we're going to draw a series of pictures here, and we're going to see if we can come up with a pattern for these standing waves. So if the string is fixed at both ends, that means that it's got to be pinned down at either end. We're going to begin, all of our drawings are going to have a pinned down spot, and that spot where no motion happens is going to be my node. So I have a string that's forced to exist as a node at either end. And as this thing resonates, as we have waves going back and forth, nodes and antinodes will alternate with each other. So the simplest possible pattern is one that flips up and down between this solid line and this dotted line. So I like using solid and dotted just to show that it's kind of, as time goes by, it's switching back and forth between one and the other, kind of like a jump rope in this case. And we have our antinode in between. So this is the first one in our pattern, the most simple one we could have. Okay. Now I'm going to define a quantity L. L is going to be the length of the string. So we're going to try to understand, based on the properties of the string, what musical note we're hearing. We're going to be interested in what frequency this produces. And in this particular case, we can see that we have a piece or a fraction of a wave fitting. And what can be helpful, I can kind of come over here to the side, remind myself of what an entire wave looks like. An entire wave is both a crest and a trough. And if we look here, we see we have either just a crest or just a trough. So this would be just a crest, would be kind of from here to here. Or just a trough would be from here to here. So what we're looking at is half of a wave. And the way that I'm going to write that, come over to the side, we'll write that L, which is the length of the whole thing, is going to be equal to half of a wave, 1/2 of a complete wave, lambda, a complete wavelength. Okay. So that's the first one in the pattern. The next one, and all of the ones in the pattern are going to have nodes at either end. So the way we go up to the next harmonic, or the next one in the pattern, is we just add another node. So there were no nodes in between, so now the next one we'll stick a node in between. Instead of having 2, now we'll have 3 nodes. The next one will have 4, and then 5, and then 6. Okay. And we'll draw a crest back through equilibrium to a trough. So we'll have this sort of a shape, and a moment later it will switch. We'll go to dotted to this sort of a shape. Instead of just having one lump moving up and down, we'll have 2. With 2 antinodes oscillating up and down. Again, if we look at this, we have an entire wave. We have a whole crest and a whole trough, which is this whole picture, a crest and a trough. Or a trough and a crest, which is also an entire wave. So we have half of a wave fitting in this. Now my string shows an entire wave, lambda, okay, the second one in the pattern. I think by the time we draw the third, we should be able to figure out what the mathematical pattern total is. So let's hit this third one here. And I expect you to be able to draw these. So we always have nodes at either end, and instead of having 1 in between, now we'll have 2. We'll have a total of 4 nodes. Node, 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 node. And we'll crest, trough, crest, something like this. And a moment later, it will switch to this, back and forth. So we have 3 lumps moving up and down, or 3 antinodes for the third one in the pattern. And so you might imagine the 11th one in the pattern will have 11 lumps, 11 antinodes. How much of a wave is this? Well, let's see. We've got a crest and a trough, which is a whole wave, and then another crest, which is half a wave. So you can see the pattern here. We've got half of a wave, we have a whole wave, and now we have a wave and a half. And if you will, we can write this as L equals 3 lambda over 2. I'll write this one as 2 lambda over 2. So I have this pattern of a half, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, and the 131st would be a 131 halves of a wave fitting into that pattern. Okay. So now that we've got a pattern, we're just going up by half waves. We can fit this. We're going to find a frequency out of this. And we come up with a way of labeling this. We're going to use the number little n and to designate which one of the pattern we're looking at. So this first one we're going to call little n equals 1. It's our first one, and it goes by the name of the fundamental frequency. Fundamental frequency. We'll get to frequency in just a moment. I mean, that's really what's going to be most important, is the sound that we get out of this. So our fundamental frequency. Sometimes this is also called the first harmonic. Fundamental frequency. So n equals 1 is the fundamental or the first harmonic. And out of all the frequencies that we hear, this is the most important. So we'll kind of put a star right here. This is the main sound you hear. So if you pluck a guitar string and it's the G string, then you're going to hear the note G. That's going to be this fundamental, this main first one. For the second one, so it's 1 half, we have n equals 1. The next one we have our little n is 2 here, so 2 halves, second harmonic, 2 halves, or a whole wave. It's above the fundamental frequency. This is called the first overtone. That's a little confusing. The second harmonic and the first overtone are the same thing. So little n is the harmonic number, and then we call it an overtone because it's above the fundamental. So I usually avoid using the word overtone. That's confusing to remember that n equals 2 is the first overtone. I like using harmonic. So n equals 1 is the first, n equals 2 is the second, just keeping me from getting confused. Okay, so the last one here we got n equals 3. This is going to be my second overtone. The second one above or over the fundamental, or as I prefer to call it, the third harmonic. And there are an infinite number of these. And knowing what these sounds are and what sounds they make, because when a guitar string or a piano string is vibrating, it's not just vibrating with only the fundamental, but these higher harmonics are present as well, which is what gives the color, the timbre, the sound to that particular instrument. Okay. So we've got a pattern here. We're going up by half wavelengths. We've got our harmonic notation here. And we can write an equation now based on what we have. So we could say in general, L is going to be equal to n lambda over 2. So it could be 1 halves, 2 halves, 3 halves, as we've seen. Okay? So for n equals any integer, 1, 2, 3, all the way up to infinity, as many harmonics as we want. Okay. What we're going to do is we're going to put that then together. Really, I don't really care so much about the length and the wavelength. I want to find the frequency, what sounds I'm hearing. So I'm going to put this together with my wave equation from the beginning of the unit, v equals f lambda. And I'm going to rearrange this equation to find frequency. So that means frequency of the sound that I hear is going to be equal to the speed divided by the wavelength. The speed divided by the wavelength. Well, what is the wavelength? The wavelength's coming out of this equation right here. It's this lambda. So if I were to solve this equation for lambda, lambda is going to be equal to 2L over n. 2L over n. So my frequency is going to be V divided by 2L over n, or n over 2L times V. So this is really where we're trying to go with all of this, is what frequency are we hearing? It's going to depend on which harmonic it is. It's going to be half waves, or half the length of the string, and it's going to be based on V, which is the speed of the wave in the string. So in terms of kind of what we'll put down on our equation card, I might write it something like this. Okay, I'm going to write Fn the frequency of the nth harmonic, so if n is 1, it's the first, if n is 7, it's the 7th, is equal to n over 2L times the speed, and since this is a string, we'll write v string, the speed of the wave in the string. Okay. Now if you like, we could also combine this with an old familiar equation, hopefully familiar equation. The speed of wave in a string is dependent upon the tension and the mass per length. So this is from our equation card, the speed of a wave in a string. Okay. And so we can see that, you know, if you pluck or strum a string, you're going to get a particular sound out of that that's going to depend on how tight the string is, how dense the string is, and which harmonic you're hearing. So other thing you'll notice about this equation is that in order to get a higher pitched noise, to play a higher harmonic, it's a multiple. So instead of n equals 1, it might be 2, 3, 4, or 5. So I can also say that each harmonic is just going to be some multiple of the first harmonic. So if I know the fundamental, if I know my first harmonic is 40 hertz, the 7th harmonic is going to be 7 times 40 hertz. So this is what we're going to put on our card, and along with that, we need to remind ourselves that the little n represents a set of integers, 1, 2, 3, 4, right, etc., for as many integers as you want. So this is what you can add to your 3x5 card. And in the next video, we'll take a look at some applications of applying this idea. And just a couple of notes about this equation, particularly when it applies to music, some things to keep in the back of our mind, we'll talk about more next time, is that generally we double n to go up an octave. So in the Western music scale, when we think about hearing the same note played at a higher frequency, hearing a high C versus a middle C, for example, we're thinking about something that's twice the frequency. That's a doubling of that harmonic. So we're going to look at a pattern of playing that same note higher and higher. The first note is going to be F1, and if I go up an octave, I'll play F2, which is going to be twice as high. But if I want to go up another octave, I'm going to play F4, which is twice as high as that. If I want to go up another octave, I'll go up to F8. If I want to go up another octave, I'll go up to F16, which isn't just a fighter jet, I guess. And so this pattern of doublings is my increases in frequency. Okay. So if you were to play a note on a guitar string, for instance, you may hear like all three of these vibrating at the same time. You'll hear the fundamental note, which is the main note. We'll hear a note that's F2, so it's going to be the same note. So say I play the E string on my guitar, I'll hear that low E, but I'll also hear a little bit of the higher E thrown in, which of course will sound nice. But I'll get a little bit of this third harmonic too. And the third harmonic doesn't fit in with my doublings. The third harmonic is what's called a musical fifth, or a perfect fifth. So it tends to be sounds that sound good together, which is why we call them harmonics.